Now then, going back to our previous discussion of borrowing the money from the bank, $20,000. What if we want to borrow it for 7 years? You have two choices. You can multiply 20,000 times a series of 1.06 numbers, which is in effect what we're doing every time we borrow the money for another year, or you can just use the equation given to you, which is what you would do, 20,000 times 1 plus the interest rate raised to, I want to borrow the money for 7 years. That's 20,000 times 1.5036, you owe him $30,000. Or, in economics, you would say, I have the present value of the money that was borrowed. I would like to change it into the value of the future money having to be repaid. You do that by multiplying F over P, and that tells you to use the F over P column, tells you to use the I% rate, tells you to use N years or payment periods. You get the same factors you do in the original equation, and therefore you owe the same money, $30,072. Now then, instead of moving money from the present to the future, let's say that I was asked to move money from the future back to the present. The equation listed in your manual for this is that P can be found by multiplying the future amount that we know times I plus 1 to the minus N. Or you can use the economics way or the eco-speak way by saying the future value can be transformed into the present value by multiplying times a factor found from the table, P over F. Use the P over F column, the I% page, the N year row. For example, let's assume that we like to deposit some amount of money in the bank, have it earn interest at 6% for 1 year, and at that time we'd like for the bank to give us $20,000 because that's how much we need for the car. We don't quite have enough for the car right now. How much must we invest now in order to have the bank return to us the money we desire, $20,000? Since F is equal to P onto 1 plus I to the N, that's what we said a minute ago, then obviously P can be found by dividing by this factor, and you get the future value can be changed into the present value. I said we wouldn't derive these, but these are so simple, probably worth seeing them. Raised to the minus N. So, the amount of money needed is 20,000 times 1 plus the interest rate raised to the minus 1 power. $18,868 would have to be invested today in order to withdraw $20,000 from the bank at the end of a year if they pay 6% compounded annually. The way we do it in economics, we say you can take the future value, change it to the present value by multiplying some factor in the table. Multiply the future value you want times a factor designed to convert future money back to present money. In that case, you would use the P over F column, the 6% page, the 1 year line. The factor out of the table is 0.9434. $20,000 times that gives you $18,000 you'll have to invest now. Same way, if you have 7 years between now and when you need $20,000 to buy the car, you can go to the table and look on the 7-year row, multiply your $20,000 times the appropriate factor, you get $13,300 needs to be invested presently in order to turn it into a future value needed. Now, another often done operation is finding how much you have to put in the bank each month or each year in order to get some desired future value. A lot of people call that an annuity. Some people call it an annual amount or an annual contribution. They all have the letter A and so we use the symbol A to denote an annual amount. For example, how much money would we have to invest annually during the next 7 years in order to be able to get $16,078.76 at the end of that 7-year period? Now, this always raises some problems, because some people say, should we assume that the person is going to run right down to the bank with the money right now and make the first deposit today, immediately? Or should we assume that having decided to do this now, it's going to take him a year to get that first payment together? It really doesn't matter. You could set up the interest rules by either saying we're going to put the first amount of money in the bank today, or will take us a year to get the money together. It doesn't matter, but we're going to have to come up with some agreement on that question, because otherwise we're going to have two sets of table. One would say 7-year investment, first payment made today, and then have another page that says 7-year investment, first payment made a year from today. So we're going to pick one or the other and stick with it. And it so happens, long before you and I got here, everybody's agreed to pick the latter. Namely, if you talk about an annuity or an annual amount, the rules will be that our equations will be derived and set up assuming that it'll take you a year to get the first number, the first money, to invest in the bank to satisfy that annual amount. Now then, the cash flow diagram then would look like this. Here's where someone has said, I'd like to find an annuity necessary, I'd like to find an annuity that I could take out of a bank given the future amount. In other words, given the future amount that I want out of the bank, how much equal values would I have to put into the bank at the end of the first year, second year, third year, fourth year? Now, another nice thing that does is that does leave this slot open for putting money in if you want to find A given P. Because in most cases, if you put in a present amount into the bank, then you wouldn't withdraw immediately that day some annuity number, some annual amount, because otherwise you wouldn't have put it in the bank in the first place. So that leaves this slot open for P. Although it does have the interesting effect of the last year you go in the bank, you have to give him an annuity. He turns right around and hands it back to you when he gives you the future value. So be careful with that. It was going to happen one way or the other anyway. We've agreed to make it happen like this. The basic equation, you want to see the derivation? I see everyone says no. An annuity can be found by taking the future value you want and multiplying it times this factor. The interest rate divided by 1 plus the interest rate raised to the number of years you're going to be able to make this investment, minus 1. That is, of course, stolen. I took that right out of the reference manual. Or you can use the economics way of doing it. Since you're given F, you can multiply it times something to get an annuity. The only way you're going to do that is to multiply it times A over F, where F cancels F, leaving you A. So use the A over F column in the book. Go to the table that has the proper interest rate. Go to the row that has the proper number of payment periods, perhaps in years. It says use the A over F column, use the I% page, use the N year row. In our case, you can look in the reference manual and look under, forget what the problem said. Said we wanted a 7-year period, so we go to the 7-year row. Oh, here we go. It was 6% interest, so we go to 6%. This really should say table. 6% table. And you will find the factor is 0.1191 when multiplied times how much you need. $200 must have been what I was shooting for. It's about as close as I could get. $199.94 each year would have to be invested. If they're going to give you 6% compounded annually each year. Now then, say we're going to find the annual withdrawal permitted given a present contribution. What if we were given a gift of $11,016.47 and you want to go put it in the bank today? You're going to leave it in the bank at 6% for 7 years, and you'd like to take out an equal amount each year. How much would the bank permit you to withdraw? This cash flow diagram, instead of having an F on the end now, has a P on the front end. Incidentally, the reason I picked the order of these to present to you is because this is the order they are presented in your reference manual, so you'll be able to just go from the top down. Find A given P. Your book